Good day to you. This is Anagalactic bringing you the collapse of the wave function. We've had to take several steps to get to the diving board because there is quite a leap. In order to get the synthesis necessary, it is necessary also to see two sides of the paradox so that those two sides can be synthesized. That's the only way to solve a paradox that I've ever been able to discover. But actually, I may have discovered, I can't confirm this, but I may have actually discovered the method of solving a paradox. Although I believe it's only one method because there are different kinds of paradoxes. What is a paradox? In the case of the quantum paradox, including the collapse of the wave function, which is part of that paradoxical system, there is a conflict of interest between two truths, both of which cannot be true together, but each of which can be shown to be true separately. So there is some context to discovering whether something is a particle, in which case it can be measured, or if it's a wave, in which case it can't be measured in the same way as a particle. A wave can be measured, but the problem with saying that is it's not any kind of measurement that we've ever made before, because a wave is not linear. That's really the definition of a wave, is a non-linear phenomenon. A particle can be said to be a linear phenomenon for the simple reason that it makes a position. Now, I taught you in the physical aspect of this paradox that in the actual universe, in what is actually physics, we have discovered such a particle in only one. Only one particle makes a position. And I've gone to such extraordinary lengths to show you that that is true. You should realize by now. It's actually a direct insight, but I don't believe anybody would contradict me. Although, you see, there are other definitions of the particle that have been introduced that do not conform to the strict definition of a particle. And I could go on into the standard model of particle physics, which has a whole host of what I would call subparticles. But in the standard model of physics, not subparticle physics, but the standard model of physics, there's no question that the atom is a unit. So the atom does make a center because it has a nucleus. And the nucleus is composed of protons, which perforce must have a center, or they could not make a nucleus. And the nucleus of an atom is the combination of all the centers of the protons in the nucleus. And nobody denies that. I'm just stating the obvious. But you really have to look at that, because they're all in the center of a system. The atom is a system. It's not a particle. The ancients called what they conceived to be the atom an atom. But then the name changed because we thought we had discovered the atom. But very quickly, well, actually not very quickly, but in quick sequence, the discovery of the electron came first, and the discovery of the proton came second. The discovery of the electron was just before 1900, and the discovery of the proton was just after 1900. But in the meantime, a lot of measurements were being made, essentially on both particles, without anyone being able to prove that they were particles. Now, the definition of a particle came about in a certain way. And so we ended up getting an interim definition of the particle, which clearly would include the proton. When any system has been developed, and this has morphed, it's evolved with time, with further measurements and further insights, the nature of the atom became clear it was a two-particle system. So there were two particles, but now you're saying that the electron is a particle. But there's a difference between the electron and the proton, whereby you cannot in the same way say that the electron is a particle. The proton is a particle. Why am I so sure of that? The reason has to do with the nature of position. Position occurs in space. tautological, nobody denies that. But can you define the position of something in space? Of course we can, but we can only do so with an axiomatic basis, because we're reconstructing space in our minds. And Bernardo Kastrup is absolutely correct, and I think profoundly correct, in saying that whatever we construct, that we call physics, cannot be physical reality. Otherwise, we would be reconstructing the physical presence of what we see. In other words, if we think of a star, the star is in us. That does not happen. That would be some kind of transmutation of material. But there is something that's conveyed into our minds that convinces us that we're seeing reality. And Bernardo Kastrup says, however you define reality, by no stretch of the imagination can it be called physical reality. I think on proper consideration, just commiseration of minds in rational logical interchange, anybody in the room, that is all of us present, which would be really all scientists, would agree that a proton is definitely a particle, but if you are pressed to say how you know that, it's because it makes a center. Because a position is a center. That's what a position is. It's a position, in our way of looking at a position, is a point. But the point has no context because a Euclidean point literally isn't even there. Not even in your mind, not even if you say so. Well, Euclid took the dare and said, you know what? I don't care if it's there or not. And he was able to prove, by a very interesting proof, that if you do say that there is such a thing as a point, which is 0D, I've proved that Euclid was wrong. But you see, that's an incomplete statement. And technically I'm wrong for saying that Euclid is wrong. I do say he is wrong because in one context he is wrong. There's no such thing as a point. I'm able to prove that now, so that's actually not debatable. But there's more to it. When Euclid said in his first sentence in Elements that a point is not there, it's not there. He then went on to show, but if you assume that it is there, I'll show you how you can retroactively prove that it is. And he proved it. That has got to be one of the most amazing breakthroughs in logical deduction in the history, and I'm not alone in thinking this. Euclid made a profound discovery, but it was not, strictly speaking, the discovery of the point. It was the discovery of how you could use an imaginary object to create something useful. And he did. It's called linear algebra. It's called linear mathematics. It's called linear geometry. Everything we do is linear. Why? Because Euclid was in no way trying to define a point. What he was trying to define was a straight line. And I think you remember from grade school how Euclid ended up defining a line. It's quite specific. And it involves 2 points. It involves 2 points. And you can't have 2 points unless you define what a point is. And so he thought about it. We can say this now. He definitely did. He said, how can I define a line in order to create the notion of distance? Because it was known that there was a relationship between distances on straight lines. That's what the Greeks were all about, was distances on straight lines. But they didn't conceive of them as numeric distances in the way we do. They didn't think of them as numbers. They thought of them as quantities. So a certain line, the baseline of a triangle, would have a quantity Now we just assume that that's a number. That's actually tautological because a quantity is a number, but it's a specific kind of number. It's not strictly speaking what we today would call a real number, which includes irrational numbers. They did not think in terms of irrational numbers at all. When they encountered an irrational number, which they did twice and it ruined everything, and what they did was they just ignored it, but they were crushed. The Pythagoreans were absolutely traumatized when they finally were able to prove that the diagonal on a perfect unit square is the square root of 2. They tried, of course, to compute it using geometry, essentially, to get the quantity. And what they discovered was it's not a quantity. It's not a quantity. It's the square root of 2, which is not even a number. Now, today, because of the introduction of the calculus, especially, it's not due to the calculus, but the invention of the calculus was strictly to solve that problem. What do you do with the fact that you can't get an exact number? You can't get an exact quantity. Well, what do you mean by quantity? This has been attacked for centuries. Cantor is famous for having attacked this problem. Because what you're trying to do is continuize a quantized space. Linear space has to be quantized in order to get a metric for distance on the quantum jump from 0 to 1, which is your unit of measurement. Well, what I showed, and this is summarizing the past 6 lectures about, or the past 1,400 lectures, because I began this 3.5 years ago, and 1,400 videos ago, by saying essentially the same thing. But you see, my research hasn't stopped. I did not realize 3.5 years ago that I was going to be solving the collapse of the wave function. That was not in my mind anywhere. I really wasn't sure what good this geometry might be. It turns out it's miraculously good. But I knew it was going to be profound in some way, because it's the world's first intrinsic geometry, which I've carefully described to you. The simplest way to state that, just using the fewest number of words, but by no means exhausting the definition, which should be ramified because this is synthetic. I discovered integral number space, which is a 2-component number system that transcends the complex numbers, which is the world's first 2-component number system. But you could say that the fractional number system is the original 2-component number system, because every fraction has 2 quantities. But they're not treated as quantities in modern mathematics. They're treated as real numbers in order to get at the space that the calculus reveals, which is, as I've pointed out, and you may have already realized this in your studies of calculus at the outset, you're cheating. You're doing what the Greeks would not do, which is you're trying to get an average that's nonlinear. But when you do that for the circle, this is where the second problem was encountered. It's not the square root of 2, it's another irrational number called pi. And pi is a killer to them. I say it's always been a killer. You will notice that in all the formulations of quantum mechanics, called the wave functions, the 2 predominant ones now are Schrödinger's wave equation and Dirac's wave equation. Both of those formulas use the irrational number 2 pi explicitly. And in the Einstein field equation and in all formulas of relativity, there is 2 pi, which is an irrational constant. That's a contradiction. You cannot have an irrational constant in a certain strict form of geometry, which the Greeks tried to adhere to and found out that they could not when they encountered curvature. The square root of 2 problem is a little bit different, although it leads to the same impasse. It's just in a different cul-de-sac, because the linear number system has severe problems dealing with curvature. Insurmountable problems at the quantum limit, which is the inner limit of measurement. Well, your instrumentation for the measurement of the smallest possible quantity in any sense, either time or space, which is or energy, you can't without transcending the notion of a particle, because at the limit, particles are not particles, although it's fuzzy. And that's a paradox. It has to be one or the other because they contradict each other. Here's how. Here's a center. It's a point. What's it the center of? Well, Euclid said it's really what I would say it's the center of a line. That's zero, is the balance point of two linear infinities. Plus infinity and minus infinity add to zero, so that's the center of this system. That's called the Archimedean of the space, in this case 1D space. And the Archimedean of the 1D space is the center of the line, which can be proved to be the additive relationship between the two polar infinities. That defines addition. That defines addition. It's strictly a linear concept. What about multiplication and division, the other pair of operators? The line defines addition and necessarily its inverse, but it's the additive inverse. So that zero is called the additive identity because it does not affect the subtraction operation or the addition operation, which are simply the polar opposites of each other. Now, in multiplicative space, it's not this, it's not polar. When two numbers are multiplied together, what does that do? We're taught in school that it creates a rectangle. And in context, there's no doubt about it. 3 times 2 equals 6. Well, you can draw that, but is that 6 in the same space? No, it's actually a differently configured 6. It's a rectangular 6, which is in area. The 2, whether it's the x value or the y value, whichever one is chosen for 2, the other one being 3, would be perpendicular. So you either get a rectangle that's lying flat or a rectangle that's standing more upright than flat. So they're perpendicular to each other. Well, that's not polaric. So multiplication is not an expression of linear polarity. It's an expression of orthogonality. And it's non-commutative. We are all taught, and all textbooks say it's mathematically. You see, you're making an assumption when you say that multiplication is commutative, which simply states that the order doesn't matter in the two-component operation. That 2 times 3 gives you the same result as 3 times 2. That's actually not true. No, it doesn't give you the same result in any sense, not even numeric. 2 times 3, if it's non-commutative, you have to take account of the fact that 2 comes first. And if by that you mean x, then 3 times 2 is not the same as 2 times 3 because you've changed the x value. You can't say, you see, and geometry proves that they're not commutative. The shapes are not the same. But we say that the area is the same. So what? That's not the same number. You fooled yourself. You're saying that 6 is equal to 6. No, it's not. Those 6's were not achieved the same way. And the reason you can't see that is because you think everything has to be a linear number. But when you're using multiplication, you're no longer using add. I think that's obvious. See, we're taught that multiplication is repeated addition. But that also is untrue. No, it's not repeated addition. It's the progressive creation of a rectangle. I don't see how you can say both at the same time. But that actually is a perfect example of superposition. It's actually consistent if you if you put numbers on top and disregard geometry, then 2 times 3 equals 6. But what does that even mean? Why are you using multiply when all you have to do is say add 3 twice to get 6, or add 2 3 times, you get the same number? Yes, because the mathematical system is consistent. But you haven't done any geometry at all. Well, mathematics is purposeless without geometry. You're just playing with yourself. You're just masturbating. You're just playing a goddamn dangerous game. The 2x3 rectangle is at no way the same as a 3x2 rectangle. Or you're saying that geometry is just shit. That is what they say. That numbers dictate geometry. So that this rectangle is identical with this rectangle. And there's all kinds of theory to support that. Well, it's nonsense. You simply cannot say that. And here's why. Here's how you can nail that down, because I'm just saying there's 2 ways of looking at this. But am I correct in saying that only my way is right? Only my way is right. I'm contradicting mathematics. You're wrong to say all the things you're saying, because you're losing information by putting numbers on top. 2 times 3 and 3 times 2 are not the same quantity in any definition of quantity, except if you leave out reality. That's what those who love mathematics really believe. They're true believers in numbers. They're insane. They're insane. And here's how you can prove that. What's the inverse of subtraction? It's addition. And the reason I said it that way was to get you to start thinking in terms of permanent relationships. Addition and subtraction are the same operation. They're exactly the same operation, except you've inverted it on the line. So is subtraction even a warranted operation? Yes, but it's superfluous. You don't need subtraction if you are assuming that there are negative numbers. If you're saying that all the numbers are positive in both directions, then you do need subtraction. Because now you need to distinguish numbers on one side of the zero or the other. Are they the same or not? If it's distance, they're all positive. They're positive in 2 opposite directions. That we have not found that to be useful, because we want the line to be continuous. It's continuous for counting addition, because if you have 2 and you subtract 3, you cross 0. And so when this idea of negative numbers was first broached long after Euclid, it was violently resisted, because you cannot have a negative quantity. But you see, if you assume that you can use a mathematical relationship between the negative and positive numbers, which turns out to be extraordinarily useful, because with negative quantities, you can keep track of debt. And you're no longer treating the line as computing distance. And it doesn't have to be used for computing distance. All right, so that is a very, I would have to say, somewhat sophistic. Is that sophistry? What's the adverb for sophistry? Sophistristic? Sophistry, whatever. It's sophistry. So I understand that this is not convincing, but here's something that may convince you. What's the paired operator with multiplication? Well, it's division. Of course. Nobody would deny that. Division is the inverse of multiplication. But is it the same inverse as between subtraction and addition? No. Because addition and subtraction are only in 1D. in its definitional basis because of the nature of the number system arranged around zero. You have basically negative distance, but that doesn't really make sense. There's no such thing as negative distance. But you can construct a situation where the distance to the star is the negative of the distance from the star to Earth. You're measuring the same distance, but in the opposite direction. If you're comparing those, you may want to have positive and negative numbers to show the difference in direction. So negative numbers are perfectly reasonable in context, but it strictly relies on add. So that seems obvious, and so what? Well, when you switch to multiplication, you have to include division. And really you need to begin with division, because division is what defines fractions. Multiplication, we don't make any kind of a dual number, but with division we do. When one number divides another number, we think we can write it as one number, called a fraction. Well, that has a specific name. It's called a proportion. And that's what a fraction is. It's not division. That's incorrect. But it's contextual, superpositional, actually. Because what you're actually saying is, when you look at division, that's not linear. It's not linear because it's not a single component number. It can be proved, and I have proved, that when you have a fraction, you're actually relating two numbers in a different way than addition. That is obvious, but again, so what? Well, the so what is, if you treat that division operation as if it were a linear operation, you will say, as we all have heard, that you can reduce that fraction. So if it's 2 over 1, oh my God, we'll all get that one right. What is the single component number equivalent of 2 over 1, which is 2 proportion 1? Is that a linear number? We say yes, I say no. You can't reduce that, or you lose information. So what's the solution to this? Well, nobody's ever seen it, but it's simply the recognition that there are two number systems. Nobody's ever seen that. Although the complex numbers have shown that we are vaguely aware of it, because a complex number is a two-component number. It has two linear coefficients. That's a change in basis system, and I don't change the basis system. What I do is I change the parameterization of the plane away from Euclidean parameterization. So instead of having two disassociated numbers except on an orthogonality, you combine them according to the rules of orthogonality, which I computed. It's strictly proportion. The two-component number system for the circularized plane is two numbers in proportion. The circle, the basic unit circle, redefinition of unit circle, the circumference of that circle is 1 proportion 1, which I say cannot be reduced because that's light speed. And you can't reduce light speed. It's 1. And that's well known. The true definition of light speed, according to top-notch mathematical physicists, or physical mathematicians, however you wish to characterize it, those who interpret physics according to mathematics agree. To get the computations you want, you have to unitize light speed. Well, that's 1 proportion 1. Instead of 300 million meters to 1 second, you simply change the designator for the units so that they match. Where 1 unit of space, however long that is equivalent to 1 unit of time. Instead of 300 million units of meters equaling 1 second of time. That's 300 million to 1. We find that convenient, but it's not at all written in the universe. It's all based on your definition of the meter and the second. Well, you can redefine those arbitrarily, such that you unitize it. Well, that's the unitization of a two-component number, and by definition, that's 1 proportion 1. So that is the definition of a circle. Now, what I was starting to prove to you with GeoGebra in the last video, which I'll simply state because now you can see it, is that when you have that 1, all numbers less than 1 are inside the 1. And there'll be two-component numbers in two-component form that we would say reduce to a number less than 1. Because the 1 proportion 1, let's say, reduces to 1. That is appropriate. It doesn't reduce to anything else, so just say it means 1. Although you're changing dimensionality when you do that. They are considered to be numerically equivalent, and we can use that to our advantage to simplify this. So you just say that the circumference is 1. But in the back of your mind, you have to realize those are two quantities, not one quantity. It's two quantities because the plane is composed that way no matter how you do it. There's only two ways to do it. Either with the additive identity, whereby the reference frame for the additive system is 0. It's the center. It's the origin. That's obvious. We all know that. But what about multiplicative space? We know that the center of that system is 1 to the proportion that 0 is the center of the linear system. Well, 0 simply is the center of the line. And a double 0 is the center of two lines. 3 zeros is the center of the 3D system. And 4 zeros is at the center of space-time. Nobody argues any of that. But what if there's no such thing as 0? What do you do then? You switch to the multiplicative system, which has a center that is a reference frame of 1. And now the center is a surface called a circle on the plane or a sphere in volume space. It's not a cube in volume space, which is what Einstein used. That may sound crazy to you. He did. And nobody denies that. He took a cube, which is 3D unit space, and he added an imaginary axis, an orthogonal imaginary axis, and then he used calculus to curve it. Okay? So that's how he got curvature into the system. It wasn't with the numbers. It was with the algebra. Actually with the calculus, which is an extension of algebra. It's a transdimensional operator. I proved that, and you would probably want that proof, but it's in prior videos. Don't worry about it here. Just we're trying to get the collapse of the wave function. Well, the photon has a value of 1 because it's a sphere. But it's not a one-component one. How many components is it? 4. There are 4 ones on a sphere because a sphere can be composed as 2 orthogonal circles, and I proved that. And each circle is a 2-component one. And when they're conjugated, they conjugate to the sphere mathematically. And that can be proved. So the sphere has a surface value of 1. That's called a unit sphere in spherical space. It's not a linear one. It's a 4-component one. It's 1 proportion 1, proportion 1 proportion 1. That will give you every single answer in physics that has not yet been seen. And I just ran out of strength. I still haven't shown you the exact collapse, so let me give you a visual portrait that I have not given you before. We have determined that the photon never ceases to be a particle. That's a hypostatic statement that I'm now going to prove. When the photon arrives, after 100 million light years, for instance, quite typical today, especially the James Webb Telescope, it's doing it daily, collecting photons that have traveled hundreds of millions of light years. That's a long way. It's also a long time. And when they're gathered, they are perfectly capable of recreating the actual visual image of where they had been. That's kind of magical. How are they able to remember all that? It's because they never change state. It's because they never change. When a photon leaves, it's got all its information forever. That can be proved, although on an asymptosis to infinity. It simply will never lose that information. With time, it continues to lose energy to infinity. But it never reaches infinity. It can't lose all of its information. So we should be able to see to the edge of space. That invokes Olber's paradox. I solved that, but I won't go into that now. That's ancillary. What I want you to see is an expanding particle. Let me just suggest something to you that goes beyond what Sir Roger said. The photon does not realize that it's traveling at all. It doesn't change. It simply it's pressurized out of the atomic system, whereby it makes what is called a quantum jump to a new particle, which is a photon. You should conceive of that as not being a wave at all. It's strictly a particle. And that can be said, but you're leaving out another aspect which we have to circle back to, which is that it's traveling as a wave, not a particle. That's commonly admitted. Christian Huygens proved it, but that's only half the answer, because it never stops being a particle. It's always coherent. And the fact that it's traveling as a wave is immaterial, which is a very good pun. So when it arrives to your telescope, it arrives as the particle. It never was the wave. It was always a particle. And when it arrives, it simply reasserts its actual nature. It's an illusion that it was a wave. In other situations, we say that the particle is an illusion. That's called the quantum paradox. This is the inverse of the quantum paradox. Because it's not doing a quantum jump out, it's doing a quantum jump in. That's the collapse. It's doing a quantum jump in. What I say is that occurs not in space, and that saves relativity, but in another context, it destroys relativity. And so it's now fair to say, and I'm going to close here with a teaser, relativity, which is really the declaration of time lag in space, is permanent. It's a fixed relationship between time and space. That's what Einstein discovered. He called that relativity because it redefines space as having a time characteristic. That's what time-space is. That's why we call it space-time. It's because it's a redefinition of space. We only see spatially, we don't see time. I want you to see time now. The photon only sees time. That's all it sees, contrary to the way Sir Roger said it. He said that the photon does not experience time. I consider that to be so profound, I couldn't get it out of my mind for days and nights. And I dreamt about it, which is common now with me, and that's not atypical for a scientist working at the edge of his own space. He starts to dream about what he's studying. I have had so many insights on awaking that I've rued the days that I didn't get up fast enough to get to the computer, and I have often typed at the computer naked. Not that I want you to visualize that. You don't need to see the collapse of my wave function, okay? But if I delayed for various reasons, which you may be able to imagine when a person first wakes up, there's several things you want to do. Get your medicine, get something to drink, take care of yourself in the bathroom. Well, in the meantime, your dream is fading because it's in short-term memory. So it's really a test of the scientist's mettle, I think, M-E-T-T-L-E. But whatever the case, I am congenial with that since I live alone. I don't disturb anybody when I go about my business, naked or otherwise, and I have often got these thoughts down. And when I didn't, I was quite frustrated because I couldn't quite regather the exact synthesis that I had achieved in my sleep. So that's just a small insight into how things can work in the mind. It did in mine, and it's not unknown. When you're talking about the flight of the photon, and Sir Roger, one of my heroes, says that the photon does not experience time, man, did I think about that. And I finally realized that the photon only experiences time. That's all it experiences. It doesn't, but time does not change it. It knows where it is in time because it's falling through time at the rate of time. Now, Sir Roger says that's why the photon cannot experience time, because it's going at the same speed of time. I say that the photon manifests the speed of time. And therefore it's the only particle that knows the speed of time, because it's the only particle that can travel at the speed of time. And it's constant. It's a constant speed. Why? It's due to hyperspheric rotation. And that involves a mind stretch that instead of going from cubic space to hypercubic space, which is what Einstein saw, I was able to see that spheric space is embedded in hyperspheric space, whereby I was then able to conjugate the two infinities of hyperspheric space in order to finitize the universe on the wavelength frequency relationship, which is a quantum of spherical space in energy units. So there's a quantum of energy called the photon, but it's variable in energy because energy levels can vary in a photon. It's called its frequency. But a proton has no variability whatsoever. It's static, which means it's spatial. And the electron, because it's not static, is non-spatial. It exists in the other universe that we cannot see. And we can compute it in terms of time. And what I proved is that's a derivative because you're linearizing time. But if Einstein showed us anything, it's that time really cannot be linearized because what he did is he made curved space-time, but he used linear time with linear space and he curved them together on a conjugality. That's the same mistake that ruined physics. He's just doing the same thing wrong again. That may not make sense. Stay tuned. Keep looking up. I will have a Quran reading in order to celebrate the new moon, which is still current, but it's nearing the end of the new moon phase, which is about 3 days long, where you have a completely dark moon. All right, you know that has a asymptotic limit at both ends, so you can't state specifically when the new moon ends, because technically it's a tempescule of time. Right? At an intersection. Correct. All right, we'll be right back. Keep thinking about these thoughts, and I'll show you the collapse of the wave function, which I'm just going to state is the transition of a particle into a system with no change in dimension. It doesn't change at all. There is no collapse because there's nothing to collapse. When the photon hits anything and is absorbed, which is called the absorption of the photon, either on the plate or in your retina, essentially. But that packet of energy is transformed back into a bound system. Well, the transition from the unbound system to the bound system is the collapse of the wave function. What I showed is that the unbound system through which the photon is traveling is exactly what we cannot see. And that makes perfect sense because we cannot see it. You cannot see a photon in flight. And that should remind you of the quantum paradox. Is it really there? It's not really there until you see it. It's not a photon until you collapse the wave function. So it's just like Schrödinger's cat. It's both alive and dead at the same time. What we want to do is show the integral solution. That's what I got. And that forces your mind to integrate itself, to see it. But it'll feel like a split because instead of using linear logic with one componency quantities, you're relating two quantities at all times, exactly one of which is not time, it's energy. And energy is composed of frequency, which is time, and wavelength, which is space, but the space is weird because it's not linear space. It's circular space, or you could not have a frequency because it's click, click, that's time. But it's time on a circle. So time is a two-component number, correct? No. It's one of the two components of the circle when the circle is composed as wavelength frequency. That'll be in the next lecture, and then you'll get it. So in the next lecture, you'll complete your journey for now. But this is a massive massive synthesis, which will boggle you at first. As you comprehend this, you'll experience the same thing I did. It's very pleasurable, but man, is it a lot. Because you're going to feel yourself accelerating beyond what your physicists and mathematicians are capable of seeing as well. They cannot see what you see. Envy my position. It's not exactly enviable. It's just the way it is. It's the nature of a discovery. Are some apple carts going to be upset? Not if you're dealing with true scientists. Are we? No, you're dealing with humans. And most of us want to make money. I just happen to be an exception by the grace of Allah. By all of his holy names. I am simply reporting what the universe told me. I know it. You can know it too. But nobody else will want to know it. That's virtually the same position as a prophet. To tell people good news that they simply don't want to hear because they don't understand it. But all they hear is, it threatens what I do know, which is comfortable. We all know that that's the major mistake of any scientist, is to be biased by prejudice. It's unavoidable if you're making money. I'm not, so I'm immune to that, but I'm not immune to psychology, and nobody is. Oh, I could still be wrong, but it would take a lot to convince me that I'm wrong now. That's about what it means to prove something. But if the proof is watertight, as mine is, it will convince a real scientist. First, you have to get that scientist to listen. But that is not always easy. Remember what happened to Galileo. Remember what happened to Einstein. Einstein was not understood when he made one of the greatest discoveries. Nobody understood it. They didn't like it because it violated standard physics. The same thing was true with the quantum paradox. Nobody liked Bohr's solution because it doesn't sound like it conforms to physics. But what if you discovered higher physics? You have to prove it geometrically. And you can't do that without mathematics. But geometry is hard to abuse because it's precise. Mathematics is extraordinarily easy to abuse now because it's linear mathematics and you just have to fudge. I hope you're convinced of it, at least partially, that I'm on the right track, but it's much more precise than that when you get to the binary numbers. That'll be next. Keep looking up. Thank you very much for staying tuned. We'll be right back.
And I mean that kindly. We're all idiots in the eyes of the universe.